Good morning to all. I am Dr. Amina Priyadarshini, Professor of EC Department, Rohini College of Engineering and Technology. Today's class, we shall discuss about the error probability of digital communication systems. The first one is the binary phase shift keying. So first of all, let us consider the binary phase shift keying. So here the binary data, the input will be the binary data, and the output will be the each bits will be indicated by different frequencies. So symbol 1 is indicated by one frequency and symbol 0 is indicated by another one frequency. So the error probability means when we are transmitting symbol 0 and we are obtaining a symbol 1. So what's the probability of that's the error? So what's the probability of occurrence of such error? That we are going to calculate. So for before that, we shall consider an observation vector capital X who has two elements x1 and x2 that are defined by the expressions x1 is equal to integral 0 to tb x of t into phi 1 of t into dt, and x2 of t which indicates that x of the limit 0 to tb x of t into phi 2 of t dt, where x of t is the received signal, so the form of which it depends on the symbol was transmitted. If symbol 1 is transmitted, then x of t is equal to s1 of t plus w of t, where s1 of t indicates the symbol 1 and w of t indicates the additive white Gaussian noise that is added in the transmission path. Likewise, if you are transmitting symbol 0, then x of t is equal to s2 of t plus w of t. So here W of t is the noise component. Here we are considered that there is a additive white Gaussian noise whose mean value is 0 and the power spectral density is n0 by 2. So now applying the decision rule on the above equation, we can find that the observation space is partitioned into two regions. That regions are denoted as Z1 and Z2. So this is a decision boundary which separates the region Z1 and Z2, which is perpendicular to the line joining the two message points. So the receiver decides that if the received signal point is in the observation vector which falls in the Z1 direction, the receiver will decide the received signal symbol will be symbol 1. And if the observation vector which x falls in the Z2 region, which the decision device will decides that the received symbol as symbol 0. So likewise, the receiver will guess in favor of symbol either in favor of symbol 1 or 0. So just consider a new Gaussian variable y that has sample value of small y which is equal to the difference between these 2 points x1 and x2. Therefore, mathematically it is denoted as y is equal to x1 minus x2. The mean value of the random variable capital Y depends on the binary symbol which was transmitted. So given that the symbol 1 was transmitted, the Gaussian random variables x1 and x2 whose sample values are denoted by small x1 and x2. The signal has mean values which is equal to square root of EB, and for x2 the mean value will be 0. So correspondingly, the conditional mean of the random variable capital Y is calculated as E of Y for transmitting symbol 1 is equal to E of x1 for transmitting symbol 1 minus E of x2 for transmitting symbol 1. So we already discussed that the signal which has the energy of root EB, so we can say it is a plus or minus root EB. So this is so far we have discussed about for the transmission of symbol 1, and next we shall consider the transmitting symbol 0, and the random variables are x1 and x2 whose mean value is equal to 0 and root EB. And therefore, when we are transmitting symbol 0, the conditional mean of the random variable y for transmitting symbol 0 is calculated as E of x1 for 0 minus E of x2 for symbol 0, so whose values are minus root EB. Next, we are going to calculate the variance of the random variable capital Y. So variance of Y equal to variance of x1 plus variance of x2, and whose value will be the power of the noise signal n0. Suppose we know that when symbol 0 was transmitted, the conditional probability density function of the random variable y is given as fy of y for transmitting symbol 0, which is equal to 1 by 2 pi n naught into exponential minus y plus root eb the whole square divided by 2 n naught. So since the condition is x1 is greater than x2, we can say that the decision is made for our symbol 1. Else, if it is in opposite case, the decision is made in favor of symbol 0. So therefore, let us consider that y plus root eb by root 2 n naught, which is equal to z. Next, because of that, the changing the variable of integration y to z, so the above equation can be written as, that is the previous equation can be written as p on 0 is equal to 1 by root pi integral root eb by 2 n naught to the exponential of minus z square into dz. So after substituting the values, the above equation becomes 1 by 2 error complementary function of root eb by 2 n naught, by which the probability of error is calculated as which is equal to 1 by 2 error complementary function of root eb by 2 n naught. Therefore, for BPSK is one of the most power efficient modulation scheme which provides the lowest bit rate for the given signal. So the energy of the signal is EB by N naught, and the probability of error is calculated as 1 by 2 error complementary function of root EB by N naught. Thank you. So finally, we have achieved the